Good morning, everyone. This is Bruce. I'm moderating this morning for our guest speaker, Larry Schofield. The subject today is on our research track, ACEC Roads and Streets research track. Larry is a retiree from ADOT. He worked for them for 29 years, and he's currently the director of pavement innovation with the American Concrete Pavement Association, and Director of Engineering and Research with the International Grooving and Grinding Association. His topic is the billion-dollar decision. Larry, take it away.
Thank you, Bruce, and good morning, everybody. And as Bruce said, I have worked for the concrete industry for about the last 15 years. But what's more important to know is I've been in Arizona since 1964 here in the Valley, and this is my home. So everything I'm about to talk to you about, I actually believe, and better than that, I can actually prove. So what the presentation is going to be about is how do you go about looking at the true cost of ownership when you're looking at replaceable surface treatments and what the other options are. So those of you who know me know I have a passion for history, so I'm going to drag you back through time a little bit. And I'm also, since no one's really seen concrete textures for probably 15 years or so, I'm going to remind you a little bit about concrete textures. We're going to talk about the quality of life issue that arose around 2002, 2003 here in the Valley, and how ADOT responded. I'm going to show you the results of the Arizona Quiet Pavement Program, and then a little bit about moving forward to our future. Just to remind everybody, the first concrete pavement was actually built in 1891, and that was 129 years ago. The picture that you're looking at on the right is Court Avenue in Bellefontaine, Ohio. And as you see it there, that picture was about 6 or 7 years ago that I took. It's now 127 years old. And the reason I say that, concrete was used in the urban areas because of its long life, and that's something that people tend to forget about. Bringing it a little bit closer to home, this hopefully is useful information people to understand on our roots. This isn't the Phoenix Freeway system, but Maricopa County started in 1920 with the biggest concrete pavement construction program in the United States. So everybody associates concrete pavement with the Midwest, but it was actually alive and well here in Arizona starting in 1920. Getting closer to the Phoenix Freeway system, this is a slide of the very beginning of it, and it was designed in concrete. And the reason for that was to eliminate replacement delays from maintenance, and also to reduce infrastructure, because if you don't have to maintain it, you don't need as much maintenance facilities. The other thing I'll remind you a couple times, the first section that went down that I'm aware of is 1960, and it's still there. So again, I'm just echoing a little bit about the long life. I'm also going to walk you through a little bit of ADOT's noise experience and research. This is the oldest ADOT noise research project I could find. And the picture on the left, I apologize, it's the best I could find because they had mimeograph back in those days, so good reproduction is not that good. But this was called a kinematic noise screen. And the concept for this was that people didn't like noise walls because it's like driving in a tunnel. So the way this is designed, it actually had slits where you could actually see through, but it actually canceled the noise. The concept is if you impose a signal that's 180 degrees out of phase, it'll cancel the sound. And that's actually the modern vehicles today. The high-end vehicles have noise cancellation technology inside the automobile. Also interesting, this technology is coming back from Europe as an innovative technology. But like I said, ADOT first looked at it in 1972. The next project was up in the Flagstaff area, I believe on I-17 in 1976, and ADOT evaluated different concrete textures to see which was the best performing. The conclusion of that research was to use longitudinal tining. Unfortunately, that's not what ADOT continued doing. They continued going with transverse tining. What I'm going to show you now is some of the different diamond grinding textures. The upper left, if you can see my cursor, is what we call conventional diamond grinding. You'll hear the term corduroy texture. In the upper right, that's called the next generation concrete surface. This is the quietest concrete surface that's non-porous yet developed to date. Longitudinal tining, as you can see here in the center. And also notice I got a little car over here, and you'll notice the longitudinal tining is in the direction of travel. What the Phoenix Freeway system was constructed with was uniform transverse tining that you see down in the lower left, and we'll get into that a little bit more. This random transverse tining was developed by Marquette University about 2000, and from about 2000 to 2010, it was promoted as the quiet concrete pavement surface. This was a huge mistake. It ended up being the noisiest concrete texture, but at that time, nobody realized that. So when I say tining, I want to give you a little bit of idea of how a paver works. If you'll excuse the Canadian flag here, this is too good of a view not to notice, but the concrete's dumped in front, discharged in front of the paver. It's extruded out, and then you have this burlap drag that goes across the roadway. And you can see it imparts a texture itself, but anytime you hear the term burlap drag texture, this is what it is. I'm going to show you a tining bridge, which would be located just out of sight right here. And that's the next picture. So when we say tines, they really are. These are little metal tines, about 1/8 of an inch wide. And I'll show you a little close-up of that so you can see it better, so you can see each of the tines there. And it's really just like taking a rake through the concrete mix. So that's when we say tining, that's really what we're talking about. And the only difference between transverse tining and longitudinal is transverse is 90 degrees to the direction of traffic. And quite frankly, that's what makes it evil. So we'll get into that a little bit more. Excuse me. So this is a photo actually taken back in the day of the uniform transverse tining on our freeway system. Again, the direction of travel is like this. What this creates is a tonal spike. What you're seeing on the bottom is a frequency and then noise level, but it's not as much the level as it is this tonal spike. This is the whine that you hear in the car that makes it where you can't hear your radio and disturbs you in the backyard. This is all a function of this transverse tining and the spacing and depth of the grooves. And if you don't accept that, I'd encourage you to go to the internet and look up the Honda Musical Road. In 2008, the Honda Corporation wanted to do a commercial and they made a musical road. So they went to Lancaster, California, and notice this is an asphalt pavement, not a concrete pavement, but they cut grooves in the roadway. And as you drive over this in a Honda Civic at 50 miles an hour, it plays the William Tell Overture or the Lone Ranger theme song.
Huh.
So you could do these grooves in any kind of a pavement material and you'll get the same result. So it is a function of the transverse grooves. Another interesting aspect, 18 days after they placed it, the city paved over it because of noise complaints. So the Honda Corporation had to move out to the boondoggles where there was no abutting properties and recreate it for their commercial. You can go to the ad. There's a number of YouTubes on it. There's a married couple that actually does a very good one, and it really sounds like it should. The other thing I want to educate you on is grinding versus milling, because when we talk with people, there's a lot of people who use the term synonymously and they're different operations. On the left-hand side, this is what a milling head looks like. And it's got a number of carbide bits that look like this. And this really is like a chisel and hammer approach to removal. This works very well on asphalt pavements. It does not work very well on concrete pavements. And I'll show you some pictures of why this is important to keep in mind. This is what's called a diamond grinding head. And the reason they call it diamond, all these little specks that you can see by my cursor, those are the synthetic diamonds that are actually on there. So it actually grinds away the material as opposed to chipping it off, and that's the principal difference. Last thing on teaching you about diamond grinding, this is that corduroy texture I told you about. So if you'll come over here on the far left, the orange is a blade. The black that's shown there is actually a spacer between blades and then another blade. The blue is actually showing you the water that is used to cool the blades during the grinding, and that's one of the functions of the spacers. But if I may take this same image and bring it back over the corduroy texture so you understand it, where you see these grooves, that's actually the blade. Where you see the ridges, that's a function of the spacer on how wide it is. And this is what a head looks like. They're stacking a cutting blade, a spacer, cutting blade, and that thing will weigh about 5,000 pounds when it's all done. So again, blade, spacer, stack it on a head. The head is mounted on the machine. This is a full surface roadway grinder. And you can see the head goes transverse to the direction of travel. It would be traveling to the right out of the page. Since most of the grinding in urban areas is done at night, people don't really get to see what one looks like, so I wanted to make sure you're aware of it. Okay, taking back a little closer to home, so you understand what ADOT went through when the noise issue first started surfacing. I tried to give you a little bit of the history on the noise. But at the time, and this is about vintage 2000, there was no standard in the US of how to measure tire pavement noise. Most noise measurements were done with wayside measurements alongside the roadway, but it collects not only tire pavement noise, but also engine noise, exhaust noise, and a lot of other noise. So there was no way to evaluate tire pavement noise. So ADOT actually had to develop equipment to do this, and I'll get into that. They constructed both concrete and asphalt test sections to evaluate them. They determined the noise levels and changes over time for each of those pavement surfaces. And after a couple of years, the recommendation was to do longitudinal tining and for the new construction, and then conventional diamond grinding on the existing transverse tining. At that time, all the ongoing concrete projects had change orders initiated to convert from transverse tining to longitudinal tining. So to kind of recap, here's what the trailer looked like. This is what's called a close proximity trailer. I know these are big words, you don't have to worry about it because you don't see these anymore, but this was the only one in the United States at the time. The technology eventually ended up to what's called an onboard sound intensity, just a fixture that bolts to the lug nuts of a car, so there's no trailer. And this is at the AASHTO standard today. So this is how noise measurement should be taken. But the reason I'm showing you too much detail is so you understand if you measured with this, which the early noise program by ADOT was using, if you measured a texture and it came in at 100 decibels, if you measured that same texture at the same time with this device, it would report it at 103 decibels. And the reason being the position of the mics are different. So when you see values of low 90s for noise measurements, it was taken with this. This is the national standard. So when you're looking at noise measurements, you should be aware of it. And also notice that these are much higher than what you would experience alongside the road because they're right down at the tire. Typically, there's about a 30 dB reduction getting to the wayside. Excuse me. One more noise basic. I want to make sure everybody understands most of the numbers we use and talk about really refers to volume. There's an A weighting applied to the decibels, which does compensate a little bit for the frequency, but frequency is an annoyance in of itself. It's like having a radio that's off station. So transverse tining actually has both of these components, and I've used this image of the awkward giraffe just to represent transverse tining because it's a different animal from the other textures. So some of the results that were done by ADOT during the time, like I said, they built two different types of test sections. Again, this is the standard that ADOT was using, and this is the one associated with tonal spike. They went in and built on 202 down by Val Vista Road about 3 miles of random transverse tining, and there was also a mile of longitudinal tining. So the longitudinal tining came out to be the best solution. It was 5 dB quieter than this transverse tining. It was 7 decibels quieter than the random transverse tining. Neither the longitudinal tining nor the random transverse have this tonal spike. But for the random transverse tining, it still was just too loud of a surface. Asphalt surfaces were also evaluated at this time. And if you look at the plot on the right, this is the rubber asphalt that was ended up covering up the freeway. This was a stone mastic asphalt. This was a polymer modified open graded friction course, permeable European mixture, and then a conventional open grade friction course. The red bars are showing May of 2002 test results, and the purple bars are showing May 2010 results. So what you can see, all the asphalt surfaces increase in noise level over time. The asphalt rubber still outperformed the others. So one of the things that was really important to know is how does that change over time? This is about, again, vintage 2000, 2001. There were only 2 asphalt rubber sections on concrete to be evaluated. Those are down on I-19 in Tucson. And when ADOT places asphalt rubber on concrete, it's 1 inch thick. And when they place it on asphalt, it's a ½ inch thick. So the only way you could generate data was to look in the pavement management system and develop a selection of projects in the same environment on flexible pavements. And so all the testing was done on those. You can see it's a shotgun blast. This is the regression that goes through it. But the important part, what was learned from this exercise, is it was estimated that the asphalt rubber will increase a 0.5 decibel per year. And when we go over the quiet pavement results later on, remember this number. So to compare what went on, again, over about a 2 or 3 year period, ADOT created noise measurement equipment. They developed test sections in both asphalt and concrete. They looked at the initial and long-term, as long as they could, results, and their engineering solution was to pick the longitudinal tining for new construction and diamond grinding for the existing surfaces. Unfortunately, it was too little too late. I mentioned we opened up the 3 miles of the random transverse tying, and that happened right at the crescendo of the noise complaints and the quality of life issues. So the governor stepped in. Communities were in support of that because they were the ones on the front lines catching a lot of the grief on the noise issue complaints. So let's take a look at the quiet pavement program. It began in earnest around 2003. It was set up with 3 different types of measurements. There was 6 research locations that looked at both community noise and also tire pavement noise. There was also at every milepost, there was collection done of tire pavement noise. And there was another set that was just neighborhood testing, with the idea is if it doesn't make much impact on the neighborhood, we don't really care what it is at tire pavement noise. The plot on the right is showing the results. This is out of the quiet pavement research program. The blue dots up here represent the existing uniform transverse tining. The average you can see was about 105 decibels. But what you also see is quite a spread. If you were, these are milepost tests. So if you were down here at this location down here as a homeowner, you probably wouldn't worry too much about the the uniform transverse tining. But if you were up here, it was chasing you out of your car in your backyard. The brown line down here shows what the asphalt rubber was at year 1 to 2. And the reason that's shown as 1 to 2 is this timeline is in relationship to when the quiet pavement program started, not necessarily the age of the asphalt rubber product. So what you'll see is it's quite a bit lower. There's about a 7 or 8 dB difference here. This was also displays less scatter. And then at year 10.5 on the asphalt rubber, that's what the gray average is. So now you can see we're down to about 3 or 4 decibels. There was actually 2 sections that had already been replaced at this time. So again, there's a couple in here that are only 1 or 2 years old, not 10. So that's why you're seeing so much scatter. But you can see you've got some of the high points for the 10.5-year-old results are right up there with as loud as the uniform transverse tining. So one of the things that I'm trying to present or relate back to the billion-dollar decision is the true cost of ownership, because that was really never done in that decision. And so I've done it myself, and I'm going to present the results for you, but it is something that needs to be done. It's usually done through a life cycle cost analysis. You evaluate alternatives for either a 30 or 50-year period. I used a 50-year period, and I compared asphalt rubber and the concrete textures. The things that you can consider for life cycle costs are initial costs, maintenance, performance over time, environmental impacts, property damage. There's a real whole slew of things you could look at. I looked at mostly the economic side and construction side, but I'm going to present some other things just so you know. If you're not familiar with life cycle analysis, the Bible was actually put out by the FHWA in the mid to late 1990s, but they have recently come out. You see this is a current date of April of this year. It's a 2-part series, but it's a webinar and it's available. Anybody who wants to look at it. So it'll help you if you're not used to it. I'm gonna get a drink here, so bear with me. So things I want to point out, I'm not going to go into the details. If anybody wants to ask, I'll be glad to share them. But for my analysis, like I said, I did a 50-year evaluation. I used a discount of 1.5%. What you'll find for, excuse me, agencies, typically 4% is what is used, but this is actually a number that came from the OMB. And I would recommend everybody to use what OMB, that's the federal government, and every year they put out a number. What this does, to give you some idea, the higher this discount rate, the more it favors low initial cost. So it's really important to get what is representative, not some fictitious number from an old manual. The other thing that this analysis is based on is a 1,500 lane mile freeway system. This was done probably about 1.5 years or so ago. And at the time, I didn't know what it was. It's closer to 3,400 lane miles. I've found out since. So quite frankly, you can double these numbers, but that's not what I'm really trying to show here. I'm just trying to show what happens when you do an evaluation. The results will come out very similar. They'll just be bigger numbers. There's two ways to present the results of a life cycle cost analysis. One is what's called net present worth. The other, what's called equivalent uniform annual cost. And what this means is this is how much it will cost you each and every year for the evaluation period. So for these numbers right here, that's telling you that's how much it'll cost you each year for 50 years. I figured this was a little bit easier for people to understand. And then I looked at two different strategies. One was new construction, meaning if I did it at the time of construction, and the other one was preservation. It's most dramatic for the new construction costs where all you're doing is doing a longitudinal tining versus putting 1 inch of asphalt rubber on. If you look over here for this strategy, the longitudinal tining is almost 5 times more cost effective. For preservation, I considered these as existing textures because there's more than most of it is a uniform transverse tining, but there are other textures that were out there. Longitudinal tining, if they could do a really good job of removing the asphalt rubber, would not need to be ground. Burlap drag probably would, but a light grind, uniform transverse tine would take a deeper grind to remove the texture out of it. So again, this stacks up. This is how much each of them would cost you each and every year for 50 years. Okay, some things that were not considered in my evaluation, but I'm going to run through them really quick, but they are important. And if you really did a comprehensive job, you need to look at all these things. You have dissimilar inflation rates, and I'll show you that. What's the best buy at construction? Property damage, damaging the existing freeway during the removal process, urban heat island, and non-renewable aggregate consumption. What you see here is starting, this graph is a time graph at the bottom, and it's showing you the timeline from January of 1971 to January of 2019. It's indexing all the costs back to 1971 dollars, so everything's equivalent. The black line is showing you the cost of asphalt cement over time, and the red line is showing you the cost of cement used in Portland cement concrete pavement over time. So typically when you do life cycle cost analysis, all the product commodities have very similar inflation rates. And so you just use a standard discount rate for everything. As you can see, that's not really true today. This was the gap in 1993 when the quiet pavement program started, and this was the gap in 2019. And so you can see that a real proper analysis would probably have to use dissimilar inflation rates for these products. The other thing is, what's the best buy at construction? When you're talking about building a new concrete pavement, it's going to cost you about $6.50 a square yard to place the asphalt rubber. And when you're placing a concrete pavement, it's all done in one lift. It's about $2.60 a square yard inch. So for that same amount of money, you could get a lot more concrete down, which would increase the performance much more. The other thing, and I apologize for the term, but I've had to replace 2 windshields, so I'm a bit bitter over it, but the property damage issue is a lot bigger number than what most of us realize. I call it black rain, and that's simply because after it rains the next day or the day, it starts to dry out. If you drive your vehicle, you hear the little dings on hitting your car of the rocks, and that's from the raveling that happens. You can perfectly see the outline of all the slabs, and that's where the aggregate's raveling. You can see 70% of the insurance claims are windshield damage. Arizona leads the nation in windshield claims, and it rose 27% here and 1% nationally. So this, if we could get a number, which I'm still trying to get, haven't been real successful, but I haven't tried real hard, but this number is probably going to be staggering, I suspect. And this is the culprit. These are the rocks that are coming out of all these little ravel places. So just a volume estimate, meaning I collected rocks from the side, figured the quantity that's coming out per unit volume, figured out the unit volume for every one of these joints. And you can see that up here, I assumed a 1 inch. It turns out to be 33.5 billion with a B fly rocks to damage windshields and auto paint. I didn't do it, but you could do the same thing for tons of recycled tire rubber released and tons of PM10 released to the atmosphere. This would take a little more thought process to get reasonable numbers, but this one's actually fairly easy. The other thing I mentioned is the damage to the existing freeway for the removal process of the ARFC. This was never considered in the time of when we threw around the idea that it'd be replaced. This is what happens. This is a worst case scenario, but this section of concrete pavement right here was reduced 1 inch in thickness. And you can see every time a milling machine, remember that milling head I showed you, that's what it looks like. Anytime it hits one of these joints, it's just going to ravel the joint. And if you look over here, this is where the milling machine stayed away from the concrete pavement. You can see the transverse tining texture, but this is where they lost control, that it got down in deeper. It raveled the transverse joint. You can see it's actually reducing the thickness of the slab itself. So this was something that happened on early on, and I'll tell you that both the milling industry and ADOT have worked very hard to prevent this, and I'll show you some pictures later on about that. So one of the things that was done by the concrete industry in 2019 was to actually go out and get profile measurements of different sections. So everything shown in black is the asphalt rubber. You can see the different routes that it was taken on. Everything shown in gray is the diamond ground surface. And this blue is actually just a section that was milled and not anything else done to it. So you can see the milling itself is fairly high. But again, you can see this is the asphalt rubber smoothness levels at that time. And more importantly, this one right here, the average of 122.5 isn't that bad, but what you need to understand is this is an average for about a mile. And the way smoothness data is collected is in 10th mile intervals. And there was 2 sections that exceeded 300 inches per mile. And for an urban freeway, that's unacceptable. The other thing that was done by the concrete industry in 2019, they hired Dr. Paul Donovan, who conducted the Arizona quiet pavement program, to come out and evaluate the sections again, simply because it's been about 4 or 5 years since any testing was done. Again, the black bars represent the noise levels of the asphalt rubber, the gray of the concrete sections. And I threw in the green one, which represents transverse tining. Fortunately or unfortunately, the contractor did an excellent job of removing the asphalt rubber, and the transverse tining came back with a vengeance, just like it was when it was original. After it was uncovered, so it still had the same issues it did when it was placed. The other thing I want to mention is the urban heat island impacts, and this is actually the source of this document. The title of their article was Streets of Fire. This was done by the emergency medical technicians, and this was done in the late 80s, early 90s, and what the practice was at the time when there were accidents, they were actually laying victims on the pavement because they didn't realize that it was an issue, but they had about 21 or 22 people that were admitted to the hospital from burn damage. And what they found was at 158 degrees, you can burn human skin in 1 second. So the EMT community radically changed their policies on how you administer aid at accidents. And this is their data, but this shows an asphalt surface. This is not asphalt rubber, it's conventional, and this is a concrete. But you can see in Arizona, the asphalt surfaces get close to that temperature. You'll also hear that the asphalt rubber cools it at night, and overall it's better. This is a picture of a ramp at Hawes Road interchange prior to it opening. This is the asphalt rubber up here. This is the concrete section down here. This is longitudinal tining. And I actually took these photos over a 24-hour period. Again, up here is the asphalt, down here is the concrete, and you can see the asphalt rubber is always hotter than the concrete pavement. So anybody can go out and do this themselves if you have an infrared camera and know a source for one. It's not magic. So one of the other things I'll mention, about a year ago, the MIT, Michigan Institute of Technology, put out a tech brief on greenhouse gas emissions. And what they did is they did it for each of the states. And the idea was that concrete has a higher albedo, meaning it reflects more light than other surfaces. So the higher the albedo, the less heating that goes on, which results in lower greenhouse gas emissions. And so for the state of Arizona, if everything was concrete, what their data shows, the greenhouse gas emissions would be the same as removing 5.5% of the registered vehicles from the roadway. So again, these are all things that have never been considered and could be considered. But this one's a little bit more important when we talk about sustainability. Everybody likes the concept of recycling tires. But the issue is we forget that 90% of that 1 inch of asphalt rubber is actually aggregate. And so for every 10-year cycle, we're consuming 424,000 tons of non-renewable aggregate. And aggregate's getting harder and harder to acquire anymore. So with the 50-year life cycle analysis that I presented, there's over 2 million tons of aggregates that's consumed. This shows the smoothness results that I mentioned. This is a concrete industry collected this day with profilers. And if you look at the average of the black and the average of the gray, you can take that back to a savings of about $665,000 in fuel savings for the consumers each and every year. Okay, where to go now? Do we want a corduroy texture, or we want what we had, and how are we going to go about deciding? So what I'm going to talk about is what I understand as ADOT's approach, because I want to give my hats off to them. I'm going to tell you a little bit about the history. In April of 2019, there was a local contractor, Matt McNeil, who said that I can remove the asphalt rubber without a milling machine, with the idea we've got to figure out some way to how to not damage the existing concrete. And he demonstrated that in April. Also in April, the Phoenix or Central District created 4 test sections on 101 out by 56th Street. This was the next generation concrete surface. This was a micro-milled surface, a skid abrader surface, and a conventional diamond grind. You can see this is a very coarse texture on the micro mill. They stopped it after 300 feet. It was supposed to be a half a mile, but it wasn't working. You can see the skid abrader really did not take out the transverse tining texture very well. Next generation worked very well, but it's more expensive than conventional diamond grinding over here. So the district selected conventional diamond grinding. In May of last year was the first maintenance project. Again, they've done this, I say at the top, pragmatic approach. So they originally started with just this little short section, 1,300 feet long, and evaluated it. When they got a little bit more confidence, came back with a second maintenance project and did about 140,000 square yards on 202 out by I-10, where you see these 2 trenches. This was one of the ways the contractor was protecting the concrete, is you actually cut the grooves in the existing asphalt rubber so the milling machine could sense the exact location of the concrete. This is what it looked like afterwards. And then the next thing was in May of this year to January of next year, there's 2 design build projects that have flipped from asphalt rubber to conventional grinding. The one on, I'll show those here in a little bit, so I'll talk to them about then. I showed you this picture before. This is the damage that can happen from the milling operation. This is the kind of condition that they're doing today. So hats off to ADOT and all the inspectors for making sure the existing concrete's protected, as well as the milling industry for figuring out how not to damage. Each and every project, the same diligence will have to be used, because like I said, it's not easy to do what they're doing. We all got to remember that, but this is extremely important, that whether it's going back in asphalt rubber, going back in diamond grinding texture, that this is what it looks like before that happens. The other thing that's a little bit difficult, so you understand some of the trials and tribulations of the owner. This is a map that the colors are relating to each of the dates of when they're built. And you come down here on I-17, you can see 1960. I don't believe any concrete was placed in 57. I could be wrong. My understanding is 1960 was the first, but this section of pavement actually used metal inserts on the contraction joints every 60 feet. And why that's important is it was a really bad design. And so by the 1980s, you had lots of spalling every 60 feet where those were at. And this section of freeway should never be uncovered until it's replaced. So the best decision for consumer is not going to be an all concrete or an all asphalt rubber system, but it's going to be a trade-off of where it's best to have long-term concrete versus concrete that shouldn't see the light of day again. So you can see the dates vary all over the place. My understanding of ADOT's current strategy is they'll remove it and watch it. And again, I applaud them, because I don't think there's an easy answer to this. The problem you have, because the concrete's covered up, there's not good corporate memory as the condition of each of these sections over time. Concrete is not in the ADOT pavement management system, or wasn't historically. Okay, experience it for yourself. These are the 2 design build projects that I mentioned. There'll be about 2 million square yards of diamond grinding that'll be available by the spring of next year. One of the things that the consumer did not have the opportunity to do in 2003, when the governor made the decision, was actually to compare the surfaces. There were no sections that were available. So now you have it, you can drive it for yourself. And I've tried to list how I see ADOT pursuing this, they're actually in MAG as well, looking for the consumer experiences. What's people reactions? What do they want? They're also going to be looking at the cost to maintain these surfaces, how they perform over time, and life cycle costing. There are no surface should get a free pass on any of this thing. And so, like I said, I think ADOT's got a very good approach on how they're going after this. Now I'm going to beat up on us taxpayers for a while because we all like to lay everything on the agencies, but quite frankly, I think the agencies are doing a really good job, and hopefully I'm going to make that aware. This is a map of the US showing the states that have enacted gas taxes since the summer of 2019. Notice Arizona is not one of those, but talking just in terms of the federal gas tax, which has not increased since 1993, what you've seen is a decrease in buying power of 30 to 40% in the money. At this same time, you've seen an increase in the wear out of your roads due to increase in volume of traffic, 30 to 50%. In the valley, it's close to 50%. And what you also have going on is the CAFE requirements, which are the federal requirements on fleet fuel efficiency. And so there'll be less gas used per vehicle in the future. Bringing that back home in 93, if we decide to build 100 miles in 2014, I apologize, I haven't updated the currently, but in 2014, you could only build 67 miles with the same money. So that's real, it's not artificial. Taking it back to consumer purchase, a Corvette at that time was basically $35,000. In 2014, it was $56,000. So on the consumer side, it costs you 63% more money to have the same kind of car. And then you're also looking at the wear out rate. Again, this is time. This is a national graph on national statistics, and this is the percent of increase from 1990. The green line is showing you the vehicle miles of travel increase. The brown line is showing you the increase in capacity. So it's obvious we don't have the capacity to change much. This is where the vehicle miles traveled were in 93. And whether this is horizontal, probably dipped a little bit. COVID, I'm sure, put it down. But eventually, long term, it's going to keep increasing. This is the CAFE requirements. Again, on the bottom, this is showing you a timeline. The vertical axis is showing you miles per gallon. This was what it looked like in 1993. The blue line represents passenger cars. The red line, light trucks. So you're looking at this was the required fleet fuel efficiency in 93. But here we are out here today, way out here. So none of these things were ever considered at the time of the gas tax, and the gas tax was never indexed to inflation. So what happens with inadequate investment? Bear in mind, we've been asking agencies to do more with less for almost 30 years now. And if that isn't a definition of insanity, I don't know. And I said, this is a taxpayer issue. We need to stand up and do something about this. This is a slide from the Phoenix Central District, Randy Everett. This is the condition of the interstate, and you can see here's the timeline, and you can see it's going down. I applaud them from the standpoint of they've been able to maintain it in as good a condition as they have, because hopefully the economics I just showed you show how difficult it's got to be for the owners. For those of you that are aware, the Arizona ASCE just came out with a report card on Arizona roads. They gave it a D+, which I thought was pretty generous, quite frankly. But I wanted to show a couple of the quotes out of their article. Is poorly maintained roads cost Arizona drivers $3 billion with a B dollars in extra repairs and operating costs. And similarly, the repair costs attributed to poorly maintained roads and bridges is reported to be more than 3 times what the cost of an increased gas tax would be. So although we may think we're saving ourselves money by not having a gas tax, the actual opposite is happening. And I told you I was going to tell you about the Arizona gas tax. It has not increased since 1991. We have the 5th lowest gas tax in the country. So moving forward, hopefully I've convinced you that transverse tightening causes noise issues in any material. If I haven't, please go to the Honda Musical Road. You'll see that it is true. It has nothing to do with an asphalt or concrete issue. It has to do with the grooving, transverse grooving. Life cycle cost analysis must be done for any major asset. You have to consider all the things of the true cost of ownership. And just so you're aware, asphalt rubber is going to require $1 to $2 billion investment over 50 years. Whether you like it or not, that's the cost. Concrete pavement requires less maintenance and can be smooth and quiet. And as I said before, an all concrete or all asphalt rubber solution will not be in the taxpayer's best interest. So I'm wrapping up here, but this has absolutely nothing to do with what I'm supposed to be talking about, but I mentioned to you, I'm a history buff, and there's a reason that Arizona is still considered one of the capitals of autonomous vehicles, because it all began here. This is a photo taken at GM Proving Ground. The first autonomous vehicle was 1953. And the one shown here is Firebird 3 is 1959. Not only was it an autonomous vehicle, but it only had a joystick, which was used for both braking and steering. So all the people who think they're innovative today, the real innovation was a long time ago. It's just technology has allowed a lot of this to become more from a practical standpoint, but there's been a lot of good things done here in Arizona. So I want to celebrate some of Arizona's successes. This is my no whining slide. This works better when it's in an audience because I ask how many people can identify what this is. And since you're not out there, I'll give you the answer before I ask them for a show of hands. These are actually teeth marks. To be particular, it's a bite mark. And the reason they're there is the guy who actually invented the phonograph, Thomas Edison, was mostly deaf. So the way he transmitted sound into his brain was by biting the frame of his phonograph. And so I use this as much as people think life is difficult today. Understand it's always been difficult. People have overcome far more difficult situations than what we have. Looks like we might have a little bit of time for questions, but if not, here's my email. I'll be glad to answer any questions, and I'll be able to, if you want more information on where I pulled up any of this information, I'll be glad to do that. So Bruce, I'm going to turn it back over to you, and now I'm going to stop sharing my screen.
Thank you, Larry.
It's going to work.
Can everyone hear me? Thank you, Larry, for the presentation. We don't have much time for questions, and I don't have any on my screen here. But please, Larry's going to be available this afternoon at the lounge. If you want to communicate with him then and have any questions or comments, please contact him there. That'll be after 1 p.m., sometime after 1 p.m. The mechanics of that, I think, are self-explanatory on the conference website. But are there any, I can maybe field one question. Is there? I don't see any. So I guess we can end this session at this point. Thank you for attending. Hope you, I'm sure you learned a lot, and I hope you can appreciate the value of research that the industry does. Thanks again. Bye-bye.
Thank you, everybody.